Okay, and welcome to another live session for the online course. Floor is open for your questions.
All right, the first question is from one of our live viewers who asks, I live in Botswana and I'm very interested to have your view on the progress of the SKA, Square Kilometre Array project in this part of the world.
Yeah, so just backing up slightly, the SKA is the next big thing in radio astronomy, and it really is a big thing. The optical astronomy tends to get the lion's share of the attention, and so everyone knows about the Hubble Space Telescope, and therefore most people also know about the James Webb Space Telescope, its successor. It's not really a direct successor because it has different capabilities and works more in the infrared. But radio astronomy is not as familiar. The current state of the art in radio astronomy has been a series of radio arrays. The classical one is the very large array in New Mexico, 27 antennae on a Y-shaped set of railroad tracks that can go from a compact to a very extended configuration. And this is interferometry, so it's designed to make very sharp radio images, but also very sensitive because each of the 15-meter dishes has a lot of gathering power for radio waves. And there are other large radio telescopes around the world. The biggest dishes are 100 meters at Effelsberg in Germany, and the Green Bank GBT, the Green Bank telescope. And then, of course, the biggest dish of all is the 300-meter Arecibo dish, which doesn't move. It's a transit telescope. So the Square Kilometre Array is a hugely ambitious project that, putting it simply, increases the sensitivity of survey radio astronomy by a factor of 100 over any present capability. So it's a huge leap forward. And it's based on hundreds of different radio antennae distributed over continental scale regions to get the highest angular resolution. And they use different kinds of spacing. There are nested arrays where the antennae, sometimes they're actually just dipole type antennae, where the dishes are quite closely spaced to get the large field of view or the large scale radio structures. And then the very largest separated antennae are used to get the finest structure. This project was announced or planned a decade ago, and the question was, where would it be? This is a multi-billion-dollar project when it's all done. There was a competition to see who would host this facility, and the two final competitors were Australia, which has a long tradition of radio astronomy going back to the Second World War, and South Africa, or rather a consortium of countries in Southern Africa, because this project is so big that it would extend beyond the borders of any one African country. And in a sort of finesse solution, if you like, both countries got the project, and so the interferometer will actually span those two different continents. And so the African part of this project is huge. It is a roughly $1 billion infrastructure project of radio astronomy that is distributed, that's primarily in South Africa, but as the questioner implies, it spreads across neighboring countries, Namibia, Botswana, and I think maybe a couple of others, but those are the three main countries. They will all host radio antennae, that will have ground stations, that will have scientific centers, that will have the ability for the general public to learn about the science. And this is the largest single scientific capital project in Africa's history. So it's a huge deal. And it's a very exciting thing for Africa. Of course, it's pure science, it's astronomy, so it doesn't aid in economic development, it doesn't translate into money in the pockets of people who still have trouble with housing and schooling and other serious problems that the Southern African region has. But it's a statement of optimism for the future. So it's a very good project, and I think the South African or the Southern African region governments involved in it are very excited that it's going to happen, because it's going to help train a technical workforce. Radio astronomy facilities don't just employ radio astronomers, they also involve a lot of engineering. So electrical engineers, mechanical engineers, there's a lot of construction work associated with a facility like this, so there are jobs created. And Botswana is one of the host countries, and again, for a fairly small country whose main wealth comes, as I understand it, from diamonds, this is a diversification for Botswana into the area of pure science. I've been to Botswana once, about 10 years ago. I had a great time. It's a very peaceful, stable, welcoming country, and I think the science investment there will be well received.
All right, the next question is from one of our live viewers, Yuri, who asks, there was a lot of speculation about mini black holes at the Large Hadron Collider, but can humans actually create black holes or not? If so, how can we use this for science?
So it's a good question. There was a lot of almost fear-mongering, I would have to say, associated with the potential to create black holes that would somehow, then settle into the center of the Earth and devour the Earth and us and everything. So these are hugely overblown fears and stories that the Large Hadron Collider could create something truly threatening or devastating. The question of whether a machine like the LHC can create a black hole, though, is very interesting, because obviously at the collision point, at the place where the LHC has targets or collides particles, enormous instantaneous temperatures and pressures are created. And so it's not ridiculous to imagine that in those tiny regions, under that enormous amount of energy and compression, you could put some region of space-time into a situation that was black hole-like. People have worked out the math of this and the physics of it, and well ahead of the construction of the LHC, in fact. And it falls short, as incredible as the energies of the LHC are, deposited into tiny regions of space. The LHC falls actually orders of magnitude short of being able to create the conditions required for a microscopic black hole. So remember, if the LHC created a black hole, it's dealing with subatomic particles. So the black holes, even hypothetically created, would be of order of the mass of a subatomic particle, like a proton or a neutron. Those black holes, of course, if you think of the compression of matter and the formal definition of a black hole, those black holes would be vastly smaller than the nucleus of an atom. So incredibly tiny black holes. And of course, they would still only have the mass of a subatomic particle, so that these are not huge threatening objects. In addition, if the theory of Stephen Hawking is correct from the 1970s, then black holes have a temperature. They have three properties. They have mass, spin, and temperature. And the thermodynamics of black holes suggest that they, by radiating energy, they will actually evaporate. And the evaporation time scale depends on the mass. The lower the mass, the faster the evaporation time scale. A sun-sized black hole will take 10 to the 68 or 10 to the 70 years to evaporate. Fantastically long time. But a microscopic black hole, the like of which the LHC might create, hypothetically, would dissipate or evaporate into pure radiation in the tiniest fractions of a second, sort of trillionth of a second. So even if the LHC could create microscopic black holes, which it can't, they would dissipate and evaporate in a tiny fraction of a second and ascend into radiation and cause no harm. So that whole threat from the LHC was overblown. Now, the more general question of, are humans close with any technology to creating a black hole? Again, the answer is no. Closer than the LHC, in fact, are large fusion lasers, so that is lasers designed to produce reproducible fusion. So these are essentially lasers, terawatt lasers, focused on one region of space, compressing fissile material to try and make a self-sustaining fusion reaction. The deuterium pellets or tritium is the light elements usually involved. And those also fall short of meeting the criteria for a black hole. They, of course, are trying to compress and raise the temperature to 10 million degrees or so of a tiny region of space to create a self-sustaining fusion reaction. They haven't succeeded in a sustaining fusion reaction, and even if they did, the physical conditions are not really close to what a black hole would be like. So the simple answer is no. Human technology is not at all even really close to creating a black hole on any scale.
All right, the next question from one of our live viewers is, if we were to explore dark energy and dark matter, what kind of probe or device could be built to collect this kind of data?
So these are, I'll separate the two parts of the questions. The exploring dark matter and dark energy are the two really fundamental issues facing cosmology. So most of the exploration of these components of the universe involve indirect observation, astronomical observation. We don't really have a physics type experiment to detect dark matter, although there are some attempts, and there's no physics type experiment for dark energy at all. But going back to dark matter, the thing we know somewhat more about, the material that does not emit or interact with radiation that outweighs normal matter by a factor of roughly 6 in the universe as a whole. Beyond astronomical observations, which involving things like gravitational lensing, which have made abundantly clear that dark matter does exist and is everywhere in the universe on all scales. The attempts to home in on the dark matter have really settled on physics type experiments operated mostly in deep mines to shield from cosmic rays, which would be a contaminating signal. And they typically involve large solid state detectors, so ultra pure cubes or detectors of pure silicon, germanium, materials like that we know how to fabricate very purely, where you're looking with photomultipliers or scintillators or various detectors at the very occasional interaction of a dark matter particle, the hypothetical dark matter particle, with the substrate, with the detector itself. That interaction is often, because they don't create or interact with radiation, that interaction is a mechanical interaction. In physics terms, a phonon is released as the dark matter particle hits a lattice of the crystal or the quasi-crystalline or semiconductor substance. And then you detect the energy released when the dark matter particle hits the lattice. So those kind of detectors of various designs and concepts have been around for years and are doing their experiments and just gathering data, building sensitivity and time on the experiment, and none have succeeded in detecting dark matter particles. So physicists are kind of stuck at this point because the kind of experiments that can be built have been built. And really all that you can do now is scale those experiments up, make the detectors 10 times more massive, which is a more efficient way to make a 10 times more massive detector for a year than to have a regular detector for 10 years. So you're speeding up the experiment. But there are no fundamentally new ways of detecting dark matter on the table. And these experiments will either succeed or fail in the next few years. And by fail, I mean that if they don't detect a dark matter particle, they will rule out significant categories of subatomic fundamental particles that are the hypothetical counterpart to dark matter, leaving physicists and astronomers with not much to choose from. Dark energy, there's very little to report. There are all the experiments designed to diagnose dark energy are astronomical experiments, and they're sort of indirect. They're looking at the effect of the accelerating expansion, which is what dark energy causes in the universe, on the rate of formation of structure, on the properties of space-time and its curvature on large scales. They're looking for potential variations in dark energy strength with direction in the sky or with cosmic time, none of which have been detected yet. And beyond that, it's actually really hard to go beyond. There are no sort of lab-type physics experiments that I've read about that can detect dark energy, as much as we know about it.
Right. The next question is from Divya, who's on with us live, who asks, related to some of these questions that have come up, what is dark matter and how does it work?
So dark matter is a substance, a physical substance, we believe, that outweighs, like I said, normal matter, which is neutrons, protons, and electrons, basically, by a factor of 6. So there's more dark matter by mass in the whole universe and on every scale in the universe than the normal stuff that we're made of, that the Earth's made of, the sun's made of, and so on. All the stars are made of. We infer its existence and its quantity by indirect means, by the fact that it exerts gravity, just as normal matter does, but it doesn't emit light. So it doesn't emit light, absorb light, scatter light, or really interact with radiation of any kind. And that's what makes it so hard to pin down. But the mass is its signature. So we detect it by gravity, by its effect on light as light travels through the universe. Gravitational lensing being the best method, because when light is bent, when space-time curves due to the presence of mass, it doesn't matter what the mass is. It can be normal stuff like protons, electrons, and neutrons, or dark matter, where we don't know what it is, but if it has mass, it curves space-time. And light then responds to that curvature of all the mass. So it's been weighed or measured on different scales very reliably and thousands of times using lensing in particular. But none of those experiments tell you what it is, what it fundamentally is. All the ruling out, the process of elimination has ruled out all sorts of things like miniature black holes or substellar objects like brown dwarfs or free-floating planets or rocks in space or tiny dust particles. And the ruling out of all these different scales of dark-ish object pretty much leaves only fundamental subatomic particle. And it's not part of the standard model of particle physics. The dark matter particle has to be a new ingredient in the standard model of particle physics, which means that it's new physics as well as exciting astronomy. There are several candidates for the dark matter particle, and as I mentioned for the previous question, experiments to detect those fundamental particles are underway and may or may not succeed in the next few years. So pretty much by elimination, that's what we think dark matter is. And if that type of particle is not discovered in the next few years, it will represent a serious crisis, both for physics and astronomy. Dark energy is in a much less well-determined state. The inference of dark energy comes really from one observation, accelerating expansion of the universe in the last 5 billion years. And that's corroborated by other cosmological observations that tie together this sort of package of how we think the universe has expanded since the Big Bang. So dark matter is directly indicated, really indirectly indicated by accelerating expansion, corroborated by other cosmological measurements, and that's essentially it. There's no other diagnostic of dark energy or no other indication as to what it is physically. And for the people who make theories of dark energy, it's a Wild West. They're looking at new fundamental theories, string theories, alternate theories of gravity. They're looking at all sorts of things. And these theories are pretty much unconstrained by observation at the moment, which is not generally a healthy situation for science.
Right. The next question is about gravitational waves, and it kind of has 3 parts. And it's from Grigoris, who's on with us live, who asks, could we detect gravitational waves from the Big Bang, and could we distinguish those from other gravitational waves? And then I'll ask the second one.
Yeah, so gravitational waves from the Big Bang are an exciting prospect or possibility. The gravitational waves that have been detected so far were if you like, the low-hanging fruit of that new field of science, because when black holes collide, or black holes and neutron stars, or neutron stars with each other, those are the 3 classic types of objects that LIGO can detect. When those objects collide and merge and coalesce, the signature, this chirp, as they call it, if you turned it into a sound, it would be like a chirp, is extremely distinctive. It's a crescendo of waves increasing in frequency until the coalescence, and then a ring down phase, or gradual dying out of the signal. So when people look in the LIGO signals in the data stream from LIGO, it's really easy to look for black hole mergers, and they've been found. The Big Bang is also supposed to have created gravitational waves, because remember, the gravity in the first tiny fractions of a second of the cosmic expansion was intense. Gravity is the weakest force, but in the fundamental physics of this, all the forces of nature merged at the Big Bang itself, and so they had roughly equal strength. So gravity and the intense gravity of the Big Bang and the intense curvature of that early space-time situation should have definitely created gravitational waves. Unfortunately, in the theories of what the signature of those waves are, they're what are called stochastic gravitational waves, which is to say they're random in their strength from point to point within that situation, and they're random in phase. If you think of the phase of an electromagnetic wave, gravitational waves have a phase too. And so And so really they're random. I mean, the fundamental word here is random. It's not exactly the same as stochastic, which has a particular physics meaning, but you can think of it that way. And those are really hard to detect because LIGO is essentially looking at noise. It's essentially looking at a mixture of electronic noise, shot noise in the detectors, and it's looking at geological noise at low frequencies, just the rumbling of the Earth, which represents a background. So the LIGO data stream, if you just stared at it, turned into a trace on a screen, is noise. And to have a noisy cosmic signature, which is not varying when time in a very characteristic way, is the hardest of all possible signals to detect. So no one's figured out a way to detect gravity waves from the Big Bang with LIGO yet.
Right, and then the final part of that question is, do gravitational waves suffer some kind of friction?
An interesting question. So gravitational waves, which essentially represent the flexing of space-time, if you like, they don't suffer dissipation. That's probably the most direct analog of the word friction. It's hard to, there's no real equivalent concept of friction in the mechanical world, where friction is usually defined in the world of space-time. So in simple terms, no, they don't suffer friction or dissipation. They do, however, of course, vary in strength as they propagate out from the source. And it's in an interesting way because gravitational waves, as they move out from their source, just imagine it's a merging black hole or the kind of situation where they've been detected so far, as they move out, these ripples in space-time propagate through space-time at the speed of light. They lower in intensity or amplitude according to the distance from the source. So if you had a source of gravity waves that was 10 times further away but the same type of object, the signal of the gravitational waves would be 10 times less. That's actually a great advantage of gravity waves because electromagnetic radiation, light, or gravity, goes down as the square of the distance from the source. And that's because electromagnetic radiation is an intensity. There's an amplitude of an electromagnetic wave, but in the physics, the intensity is the amplitude squared. And so that inverse distance relationship for amplitude, or gravity waves, turns into an inverse square relationship for intensity of electromagnetic waves. And that, of course, means they decline in strength, in detectable strength, much faster from the source. So gravity waves, therefore, inverting that logic, can be detected at very large distances in the universe, which is why we shouldn't be totally surprised that the gravitational events so far, a handful of them, are distances of 1 billion light years or more away from the Earth.
All right, our next question comes from a viewer who seems generally interested in space-time phenomena. And the questions from him are things like, can you please talk about what an Einstein-Rosen bridge is, a wormhole is, or have we ever found a rip in space-time? So those kinds of things.
Yeah, I'll just bracket all these things into one category because they are all essentially structures or features in space-time. So the backdrop comment, which is quite relevant because these things are hard to calculate, is that general relativity, the formalism of general relativity, as defined by Einstein and used by theorists for a century since, involves space-time being a smooth continuum. So obviously general relativity accommodates space-time being curved, and you can think of a black hole as being a region of space-time that's pinched off from the rest of the universe by an event horizon. But generally space-time is smooth and continuous, even though it can have curvature and even extreme curvature. And in fact, that's part of how you calculate. And to apply general relativity to real physical situations, you're relying to do the calculations, which are difficult anyway, on the fact that space-time is smooth and continuous, even though it may have curvature. If you acknowledge or ask the question about ruptures in space-time, rips or tears or holes or however you want to call it, then there's two issues. One is the calculation issue, which is actually really challenging. So in general relativity, it's extremely hard to do calculations of these kind of more chaotic space-time situations. And in fact, normal theory, you know, pencil and paper, if you like, equations, is really hard to do. You have to use approximations. So it's numerical relativity. Most progress in even considering an Einstein-Rosen bridge or a wormhole or these has been made with computers, with computer simulations of relativity. That's really the only way to make progress. So that's the theoretical situation. Then the observational situation is, where would you look for such situations? We think black holes are real. We've now got pretty compelling evidence that they're real from gravity waves. And we've found black holes on various scales, from 10 times the mass of the sun to 10 billion times the mass of the sun. But we haven't so far found any situations where there are literally junctions in space-time, or holes or seams, or you know, these kind of more extreme space-time features. And it's not even totally clear what the signature of these features would be. They're hard to look for, and it's not clear what the signatures would be. And it's also not clear what physical situation would create them. So in general, the universe, although general relativity talks about curved space-time, the universe is essentially pretty dull for the most part. Space-time is essentially smooth, uniform, and flat on almost all scales in the universe. The black hole situation is very unusual, and it applies on very small scales for some finite and small number of objects in a universe that has 100 billion galaxies and trillions of stars. And there are not that many black holes. And nobody's figured out a way to look for these more extreme gravity situations. So they remain in the realm of theory and speculation.
And one last question related to this. Is there any evidence of the existence of white holes?
No, there's no sense yet that a white hole is hypothetically a situation, you know, a twinning of a black hole and a white hole, a place where you've sort of, you know, if you want to imagine the analogy of rubber sheets and so on, you've pinched two disparate parts of the sheet together and connected them. And so you can have energy or mass flowing into one place and then emerging in another place at a very different point in space-time. Very interesting. It would allow for sort of space-time travel, if you like, if that were possible. Now, you could say a white hole is just a place where energy is coming out of a small region of space, no bigger than a black hole. And then you could imagine that any place where that's occurring might be a white hole. But there's no, you need a lot better information than that to declare a white hole, since it represents a very extreme gravity situation and implies an interconnection of space-time across large distances and or times. And the energy we've seen coming from the region where we think black holes exist is all explained in terms of accretion disks and matter falling into the black hole and swirling around it and getting accelerated and getting heated up. And that all happens well outside the event horizon. So the simple answer is no. Nobody's ever seen anything that they could plausibly claim is a white hole. And nobody's really been able to calculate a unique signature of a black hole that would distinguish it from some other astrophysics phenomena where energy was coming out of a small region of space.
Right, our next question from a live viewer is, can there be a new propulsion system which could achieve speeds shown in sci-fi movies?
Well, sort of two levels to this. If we're stuck at slow speeds, I mean, I can't remember the actual number, but in terms of NASA spacecraft or spacecraft in the solar system, the fastest velocity we've created for any man-made object is a tiny fraction of the speed of light, really thousandths of a percent of the speed of light. Tiny. I mean, it's absolute fast. I mean, 10, 20 times faster than a speeding bullet, and obviously highly supersonic, but a tiny fraction of light speed. So we're stuck in the doldrums as far as accelerating any physical object to even a tiny fraction of the speed of light. So the step we're hoping for in the next 50 to 60 years is not going to happen in 5 or 10, is to be able to accelerate maybe tiny probes like nanobots up to a few percent of the speed of light. A project called Breakthrough Starshot, which was announced to great fanfare about a year ago, aims to visit the Proxima Centauri system, our nearest star system, with tiny space probes, nanobots, maybe 1 gram size spacecraft with sensors, miniaturized sensors on board, which maybe have solar sails attached, and you accelerate them with the sun's energy to some significant speed, a few percent of the speed of light, maybe 5% of the speed of light, and then the reverse process decelerates them when they get to the nearby star system. So that's absolutely bleeding edge project that was announced, and some of those technologies don't exist, and none of them have been demonstrated, and that's just to get to like 5% of the speed of light, and that's considered to be a 40-50 year project that they're just starting out on that road. So that's sort of where we are with traveling a lot faster than we are now. I mean, it's decent. That's 1,000 times faster than the fastest spacecraft for a tiny probe, but it's still far, far less than the speed of light. So I don't consider that sort of science fictional or Star Trek-like. Star Trek-like would, of course, be near light speed or faster than light speed travel. And unfortunately, the laws of physics are an almost implacable obstacle to that. As far as faster than light travel, there's simply no place in conventional physics for the reality of faster than light travel. Essentially breaks the laws of physics that we trust pretty well after 100 years. And even to get close to the speed of light, 90-95%, for any physical object that you could see, even a 1 gram nanobot, would take a phenomenal amount of energy. I think the calculation is that to put one of these tiny gram-sized nanobots to half the speed of light would be more than the energy consumption of the US for a year. So these are really difficult constraints, and so science fiction for now remains science fiction.
One of the students heard you mentioning that you had been to Africa and wanted to know if you had visited Uganda.
I had not. I've been to South Africa a few times, and I've been to Kenya, and I've been to Egypt, and I've been to Namibia, and I've been to Botswana. I can't remember all the places I've been now. So I've been to West Africa, a few other places in West Africa, but not Uganda. I'm actually going to late next year on a sort of human origins and astronomy origins trip to South Africa and Namibia, and we're going to visit the SKA, the telescope that was being asked about, which will, at that point start to have some dishes being built, so there'll be something to see.
All right, our next question is from a live viewer who asks, is the expansion of the universe an increase of the volume, or could everything just somehow be changing places?
Yeah, that's a good question. So in the conventional thinking of cosmology, it is an expansion of the volume. That's the simplest way to put it. So in some region of space, if you just imagine going beyond the Earth, like beyond the galaxy into deep space between galaxies, you can visualize space-time, three-dimensional space-time, which is essentially smooth and flat. So you can think of Euclidean non-curved space-time. And if you had imaginary markers in the space-time, just marking out a three-dimensional grid, those markers would just move away from each other, and that's the expansion rate. And so it's expansion in a volume. I mean, you can measure the distance between any 2 points, and it's increasing, and the volume will be increasing as the third power of the distance increasing. Again, because it's linear, it is actually pretty much the third power. There's no indication, again, in the standard cosmology, that there's rearranging of pre-existing space, or that the expansion is taking place into a larger situation, an enclosing space-time. No indication of that. All the evidence we have is that the expanding space-time that we occupy is all there is in the universe. And so we see around us our part of the expansion, and as we look further out with telescopes, also back in time, we see other aspects of the expansion, but the entire entity is doing essentially the same thing all at once.
Rami, who's on with us live, asks, what are the pros and cons of the SpaceX StarLink internet network?
Well, the SpaceX, because they're at the cutting edge of moving us beyond the Earth, into sort of semi-permanent habitation, certainly in Earth orbit, and then eventually on the Moon and Mars. SpaceX, as we know, has the ambition to take people to the Moon and Mars. And Blue Origin's, the Jeff Bezos company, which is the direct competitor to SpaceX, has similar goals. Well, these companies realize that as we start to build a, permanent presence beyond the Earth, and for the moment, all we have, of course, is the space station. The International Space Station has been continuously occupied by a range of astronauts for 15 or 20 years. I can't remember how many years. That's low Earth orbit. That's, a few hundred miles away. But as we go much beyond the Earth, the issues of communication will become quite significant. And so NASA was in the cutting edge of this, of working out what the requirements or the spec would be on an interplanetary internet. That is an intranet or sort of data transfer that could work throughout the solar system. And SpaceX, they didn't really do the pioneering work in this. NASA sort of did the pioneering conceptual work. SpaceX are picking this up, and the question alludes to their project because for them it matters too. As astronauts and SpaceX clients start to be beyond the Earth, their ability to communicate seamlessly will be just as important as it is for us on Earth. And the standards for the space-based internet have not yet solidified. There's no sort of governing body like there is on Earth. So on the Earth, we're moving from 4G to 5G speeds. In space, the constraints of power typically, and then the dissipation of signal over distance, there's nothing even close to the data speeds we're used to on Earth, especially the ones we're going to get used to with 5G. And so these internet protocols beyond the Earth are really struggling against the capacity of the technologies to deliver high bandwidth and significant power because the distances are so large. Think about it, on the Earth, we have satellites beaming information, but cell phones, the ubiquitous cell phone depends on towers, repeaters, essentially, that can, that litter the surface of the Earth, that give you your signal, and they're close. Out in space, you don't have that network of towers. You don't have repeaters. You don't have signals being propagated and amplified, and you have huge distances, hundreds of millions of miles. So this is a huge problem. The power requirements are quite intimidating, and so nobody solved it. And so SpaceX, like everyone else, is trying to work it up from the ground up, and they're trying to, of course, use really cutting-edge technologies to do this because the demands on the space internet, if you want to call it that, are much more stringent and severe than they are for terrestrial internet.
All right, the next question is from Donna, who is on with us live, who asks, what are your thoughts about the holographic universe theory?
So the holographic universe theory, it's been around for a while. It's a pretty hypothetical situation. It extends from an idea that was applied and developed for black holes, actually back in the late 70s and early 80s, the sort of glory days of black hole theory around the time of Stephen Hawking and others at Cambridge. And the holographic theory applied to black holes implies that there's information trapped or stored holographically in the event horizon. So that two-dimensional membrane called the event horizon, while marking a boundary between where information can exist beyond the black hole and where information cannot be accessed, that boundary might have the information of what fell into the black hole somehow coded on it in this two-dimensional surface. And the holographic universe idea is a simple extension of that idea, which says that the universe itself, whether it's the very early universe in the Big Bang, because remember, the cosmic expansion has the equivalent of event horizon, has a region beyond which information cannot be accessed. The holographic universe is a statement that perhaps that information that we can't normally see because of light travel time and propagation effects is actually accessible and is actually coded into what amounts to the event horizon of the expanding universe. So it's very, very speculative. There's really not even a way to test it at the moment, and there's no way to test the holographic principle applied to black holes either. So it's a cute idea. It has some physical basis, I would say, in gravity theory. But it's pretty much in the realm of speculation still, 15 years after it was first developed. All
right, our next question is from Richard, who is on with us live, who asks, is there any more recent evidence for Planet 9, the one that is supposed to be 20 times as far from the sun as Uranus?
No, and the searches are continuing, so that this will be a short update because no, there isn't. It will be front page news if Planet 9 was confirmed. Looking that far away from the sun for something that may seem large, compared to human scale, but astronomically is quite a small object, that's a really hard thing to do, especially something that's going to be dark. And so surveys for Planet 9, these surveys are typically looking for a lot of different things that would be not very cost effective to just have a huge survey and facility just to look for Planet 9. They've come up dry so far, and there's basically a lot of skepticism that anything like Planet 9 exists or is even required or called for.
All right, the next question is from Glenn, who asks, what are the implications of the budgetary cancellation of the W-FIRST telescope for U.S. space science?
Yeah, this is a bit of a concern for astronomers. The astronomy federal budget situation is, fluctuating. The last two presidents' budgets have, really been kind of harsh to science in general, and not as harsh to space science and astronomy as to climate science. But they've been pretty harsh, significant cuts or flatline budgets at best for NASA. And so these big new projects have not been faring well. I mean, we obviously are in a fiscal crisis of some kind. Independent of the president's budget, Congress is still under these spending caps, these sort of mandated caps on spending, on discretionary spending that were put in place a decade ago and haven't been lifted. And so even with flat budgets, your purchasing power is just declining year by year. So federal agencies, just don't have a lot of new capacity. W-FIRST was an exciting project. It was sort of opportunistic because it emerged out of the fact that astronomers did want a successor to the Hubble Space Telescope. And I'll rewind to what I said earlier about James Webb. James Webb is not a direct successor to Hubble. It's not a direct successor. It's bigger, 6.5 meter mirror compared to 2.4 for Hubble. But it's not a successor because it really moves the science into the near infrared, a different regime, a different realm, enabling it to do some kind of science that Hubble couldn't do so well, but also taking away some science that Hubble did well, and with short wavelength of light and the ultraviolet especially. So W-FIRST was a more literal successor to Hubble of enhanced capability, better sensitivity, bigger CCD arrays, more light gathering power. And it was opportunistic because it was based on the sudden availability of mirror, at least one blank and possibly a second, from the military. The military have been making light, super accurate mirrors for tracking satellites, essentially for security purposes. These are classified projects to count nukes on satellites to make sure the Russians are not violating the test ban treaty and other things. And so this military blank that wasn't going to be used for a military project essentially dropped back into NASA's lap and left the possibility, since the biggest and most expensive component of the telescope had come for free from the military, of really putting a new project into place. And the W-FIRST, the WF really is the key part of the acronym because it stands for wide field. One of the few deficiencies that the Hubble Space Telescope has is that the CCD arrays in it, in all its instruments, in all their various upgrades, are still fairly small. Hubble looks at postage stamp areas of sky, not literally postage stamp, but very small fields of view compared to even most ground-based telescopes. So W-FIRST was an attempt to go to Hubble depth or better over much larger regions of sky and be able to do surveys like hundreds of times Hubble's field of view. It's very exciting, enabling new kinds of science, different kinds of science, and because you could work at short wavelengths, even into the ultraviolet, those wavelengths are not available from the ground, so unique science. So astronomers got pretty excited about it, and it seemed like a good deal because the mirror was already there, and NASA was enthusiastic, and various panels weighed in and said, yeah, it's a good project. And so it's moved up in the reckoning for the next decadal survey, which is the astronomers' 10-year definition of what the big projects are, what the priorities are for the upcoming 10-year cycle. And that's sort of now been derailed by budget reality. And so it probably WFIRST was lowballed a little bit in terms of its expected cost. And as people got a little more realistic about what the cost of WFIRST would be, it started to look a little less plausible. And then combined with the budget realities, the lack of any new money in the astrophysics budget, it's now been called into question. And of course, there's been at least one, and I think maybe a second panel report that have just decided that maybe, you know, it was overly ambitious, that it couldn't deliver on its goals, that it's going to have some technical challenges. So WFIRST is kind of in limbo, in a pretty uncomfortable limbo, actually, where it might actually be canceled, because if you do WFIRST, there's a lot of other things you won't be doing since it's pretty expensive. And if WFIRST has these serious questions attached to it for technical reasons, then you better be very sure that it's a good project and the one that all astronomers want. And that's not the case as we speak.
So this is a really interesting question that I haven't seen before from David, who's on with us live, who asks, what is the rate of expansion of the universe, like in everyday terms? If we have 2 points spaced 1 meter apart, how fast is that meter separation increasing?
Right. Well, I hope I'm going to be able to do this in my head down to a conventional scale, but the Hubble constant, so the metric of the size, scale, and age of the universe, because you trace back the expansion rate to get an approximation for the age, assuming linear expansion, is the Hubble constant. It's velocity divided by distance. It has the dimensions of inverse time. And in the units that astronomers measure the Hubble constant, and it's now measured to a precision of 4 or 5%, so it's one of the more accurate cosmological parameters. In round numbers, it's about 70 kilometers per second per megaparsec. So that means that if you had 2 points a megaparsec apart, which is 3.26 million light years, they would be moving apart at 70 kilometers per second. And so if you want to, and everything just scales linearly because it's a linear expansion. So this is where I'm going to have trouble doing it in my head. But if you wanted to scale down to 1 parsec, that's a factor of 1,000,000. So you take your 70 kilometers per second down to 70 millimeters per second. So on sort of the distance between 2 stars, few light years, the distance, those 2 stars by space-time expansion are moving apart at like a centimeter per second. That's the rate at which their distance. And if you think about it, those 2 stars are 100, tens of trillions of miles apart. So this is pretty subtle. So for 2 nearby stars in the galaxy, just think about our galaxy. That's a little awkward because our galaxy is held together by gravity. But if you could imagine just 2 points in intergalactic space that just happen to have, free-floating stars sitting there that were marking the expanding universe, those stars that were at a distance of the typical separation of stars in our galaxy, like us to Proxima Centauri, they're moving apart at a centimeter a second. Pretty imperceptible.
Excellent. Our next question is from a live viewer who asks, what changes and challenges will we be facing when we start colonizing Mars?
I'm glad to have a question from a live viewer, because the questions from the dead viewers, they just don't quite measure up. So when we colonize Mars, which I, along with a lot of other people, believe eventually we'll do, huge challenges. It's an incredibly expensive and dangerous undertaking. It's going to take decades just to have enough missions to sort of prove the vehicle that would take astronauts back to Mars and from Mars. At some point, obviously, the colonists may just stay there, live and die there, and new generations be born there. But I'm sure that's 100 years before you're in that situation. So for the development phase, you have to be able to build a base, and you have to ferry stuff there, and you have to ship people there, and you'll have to bring them home. They're not going to stay there for their whole lives. They'll spend tours of duty there, 3, 4, 5, whoever until they go crazy, it may be very hard to spend more than a few years there. And so this is probably going to be dozens of missions. Now, to make it even halfway plausible, you have to what is called live off the land. It's so expensive to raise things out of Earth orbit, the rocket fuel cost of that, that you obviously, apart from the people themselves and some critical materials, you really don't want to have to ship the whole building materials and all that. I mean, that's basically ridiculous. You absolutely don't want to do that. So a Martian colony is really going to be predicated on building most of the infrastructure on Mars. So a lot of the early construction is actually going to be based on building fabrication plants, which you can think of as extremely sophisticated 3D printers, because the 3D printing technology is developing very quickly. And those, and that's the key ingredient, because you put the energy and the money into developing a fabrication capability on Mars, very flexible, like a 3D printer, of course, which can be programmed to generate all sorts of components. Raw material, you obviously need the raw material to come from Mars, so you're going to be mining the Martian regoliths. Your building material is going to come from the Martian soil itself. You're going to use the Martian soil to get your water initially, because we know there's water under the surface. You may be drilling down tens of meters into an aquifer or of ice that's we know is under the surface, and not too far under the surface. We know places in Mars where there's substantial volumes of frozen water tens of meters down, maybe hundreds of meters down. So that will be a critical first part of the infrastructure there, a sort of rig that can routinely let you mine ice and melt water and store it. You're also going to be taking Martian materials and using simple electrolysis and chemical processes to generate oxygen. So then you're going to be liquefying and storing that. So the first wave is not going to be, just sending the colonists there and it's a reality TV show and they're just going to live and die and talk back to Earthlings about what it's like. You're going to spend probably a couple of decades building that infrastructure to even construct a habitat for even, I don't know, 6 or 8 people. And that's, that's going to be a little mundane. It won't be as exciting to watch, but it's basically what you have to do to make it even partway financially feasible. You have to use the local materials. And those technologies are actually, the good news is those technologies are not, the 3D printing, the fabrication capabilities are moving very fast on the Earth, and we essentially know how to do that. We know how to get the water out of the soil. We know how to get the oxygen out of the soil. We know how to create building materials that could protect a habitat from cosmic rays in the harsh environment. We know how to do all that. The hydroponic part, the feeding yourself, I mean, forget about The Martian, but go back to the book, The Martian, which in the details of the book actually, in a very knowledgeable way, it's not just potatoes. There's all sorts of things you could grow on Mars, and pure hydroponic cultures would actually let you live very in an energy efficient way. So those things are going to be the process and the path. And like I say, I bet it's even if we got going now, it will be 50 years before there's the first hint of a viable colony.
All right, we have 5 minutes left, so we'll try and squeeze in 2 questions. The first question from Raquel is the entropy in the universe increasing or decreasing? And if it's decreasing, what about the second law of thermodynamics?
So entropy for the universe is an interesting concept. I mean, entropy colloquially to most people means disorder. And in the physics terms, it's the number of equivalent microscopic states. If you have a system with a large number of equivalent microscopic states, it has a large entropy, and inverse is true. So in terms of the universe, the entropy of the universe is increasing. So the universe is following, as a whole, is following second law of thermodynamics. An example of that is black holes. As matter collapses and some parts of the universe turn into black holes, a black hole has a black hole that's the mass of the sun has 100 million times the entropy of the sun itself. And so the progression of the universe to forming collapsed objects like black holes is a manifestation of increasing entropy and disorder. And as stars end their lives and turn into, as they dissipate their material, blowing some into space where it becomes uniform, and then a collapsed core, that also is a net increase in entropy. So overall, the universe is increasing its entropy. The puzzle, just to leave the question with another question, is that the universe, the absolute amount of entropy that the universe has as a whole is low. It's remarkably low compared to what it could possibly be in all the possible universes you could imagine. So, in other words, this is a relatively highly ordered and not chaotic universe, which is interesting. You know, you only have one universe to judge and to live in. So, is that a coincidence? Is that something we should explain with a theory? Nobody knows.
Right, and our final question for today is going to be from Rarashi, who is on with us now, who asks, can you tell us about the Great Attractor?
So the Great Attractor is a large concentration of mass involving, I think, tens of thousands of galaxies, maybe hundreds of thousands of galaxies. It was identified in the 70s going into the 1980s. Some very prominent astronomers. There was a group called the Seven Samurai. It's a very grandiose name for astronomers who don't really have samurai culture or ethos in any other way. So, and two of those Seven Samurai worked in Tucson. They were doing galaxy redshift surveys, and as they surveyed the redshifts of galaxies and their rate of expansion following the expanding universe, they started to see anomalies that indicated a concentration of mass on a very large scale. So people were familiar back in the 70s and 80s with clusters of galaxies and even with the idea of superclusters, but they saw something, velocity anomalies in the flow patterns of galaxies that indicated a structure that was truly phenomenal. I think it had 10 to the 16, one with 16 zeros after its solar masses, which is literally tens of thousands of galaxies in one super large region of space, maybe 50 to 100 million light years across. And at the time, that didn't really have any expectation in theory. How could the universe have created a concentration or an overconcentration or an overdensity on that scale? As time went by, it turned out the Great Attractor was not quite as great and not quite as monolithic, single object, single concentration of gravity that they thought. So the dramatic nature of the Great Attractor as it was first claimed has sort of gone away with time. And it turns out that the concentrations of matter that they saw do have a normal explanation in the theory of gravity applied to an expanding universe. But it was an interesting indication back in the early days of galaxy surveys that nature had formed gravitational structures on vast scales, like I said, 100 million light years. So it was a pretty impressive piece of work. Okay, well, great questions as always. Thanks for your questions. We'll be back in a couple of weeks.
You also mentioned that.
Oh, yeah. Oh, yes. And today and in general, we always like to mention that there's work behind the scenes and the behind the camera crew. Today, we have Melody Hardegree-Ullman, who's an undergraduate working with us on this and lots of other things. And Matthew Wenger, who you should be familiar with by this point. He's the education program manager for my project, and he's heavily involved in the creation of this MOOC. So we acknowledge the many hands that go into making these and look forward to talking to you in a few weeks.